the garage gets a little cooler and the refrigerator gets a little warmer. That makes sense, doesn't it? So when they ask you that question on the AP exam, give yourself a little sanity check. Does it make sense to go from cold to hot? No. Okay? So, back to this. We have delta U again. W is the key thing. You guys are going to have a plus there, so you need to evaluate the W according to the plus. Like I told my guys, make the equation work with what sign you put in front of the W. Okay? So, if I'm doing work on a system, let's say I've got a cylinder here with a piston at the top, and I can press down on the piston. I've got a gas inside. When I press down on that piston, what's going to happen to the internal energy inside that container? Is it going to go up or down? Up. So if I'm doing work on the system, what sign does the W need to be? Positive. Positive. If this is a plus, okay? If that's a plus, if I do work on the system, I want U to get bigger. So W needs to be a positive number if I'm doing work on the system. Okay? If the system is doing work on the piston, in other words, it's moving the piston up, increasing the volume inside the container, what's going to happen to the energy inside? It's going to go down. There's more room in there. That's going to go down. Okay? So what do I need the W to be? Negative. So now I've got Q minus W, so the U goes down. So think about it logically. If I decrease the volume by pressing down on that piston, the gas energy is going to go up. Make that positive. If the work is being done by the system, pushing the piston up, now the energy in here is going to go down, and that needs to be a negative number. You with me? I told my class, in my youth, I was a Star Wars guy. The first Star Wars came out when I was 10, okay? When I was 10. So I always think about Luke Skywalker and Princess Leia in the trash compactor, right? All of a sudden the trash compactor starts coming in and they're scrambling all over the place. Their energy has increased because they're about to get squished. The molecules do the same thing, okay? So that's how I keep it straight in my infantile mind. Okay, now, over here. Okay, all right, yes sir. I didn't see that episode. I don't know. Okay, here we go. Thermal processes. Okay, we got 4 separate thermal processes and they're really important. Isochoric, isobaric, isothermal, and adiabatic. Okay? We're going to look at their graphs here in just a second. As the light goes down, maybe we'll be able to see it a little bit better. Okay? Isobaric process occurs at a constant pressure. And we're going to talk about these formulas here in just a second when we look at our graph. Okay? So this is isobaric. I know some of you have a hard time seeing this. This is isochoric. Isochoric occurs at a constant volume. Constant volume for choric. Okay? We'll have this formula here again. We'll look at that when I put up your graphs in just a second. Isothermal is constant temperature, and adiabatic occurs without the transfer of heat. When you hear adiabatic, if you have an adiabatic container, it's not allowing any heat out and it's not allowing any heat in. So would something like copper be a good adiabatic container? No, because it's going to heat up to what the temperature is on the inside and it's going to release heat to the outside. Not a very good adiabatic container. It's a better diathermal container. It's letting temperature, letting heat out. It's diathermal. Adiabatic doesn't allow the movement of that heat, whether out or in, either one. Okay? All right, so we're going to come back to these processes. Finally, the second law of thermodynamics, we talked about this one earlier. Heat or energy flows spontaneously from hot to cold. We talked about that with our example of the garage, okay, in the refrigerator. Third law of thermodynamics, it's impossible to reach a temperature of absolute zero. Because what happens once we reach a temperature of absolute zero? All molecular movement ceases. And if you can do it, we haven't been able to do it yet. Yes? Yeah, they've gotten pretty close. And I don't know. Yeah. Okay, so they've gotten close, but they hadn't gotten there. Okay? All right. Okay, let's look at these graphs. Okay, now, these graphs, okay, these graphs and these pictures are in your book. I'm sure that you've seen them before and looked at them. I drew them up here so we can point at it a little bit as best as you can see and describe it. Okay, this is an isobaric process. Well, how are we making it isobaric? We're applying a constant pressure. So what's being done here? Well, we have a cylinder. Inside the cylinder is a piston. It's got its own weight. It's going to apply a constant force down, isn't it? And its area is not changing. Remember that pressure equals force over area. Agreed? All right. So if we're not changing the force or the weight of the piston or the area itself is applying a constant pressure. We've also added a block on top. That's got weight. Again, constant pressure, and then any barometric pressure, atmospheric pressure that's coming down on the top of that piston. All those things together are applying a constant pressure on the contents inside the cylinder. Now, we're going to heat it up. So we're adding in Q, aren't we? In our formula, delta U equals Q plus W, we're adding Q to the system. And when we do, this piston starts to move up. So the volume is changing, isn't it? We're getting a change in volume without a change in pressure. So when we graph that down here, volume, VI to VF, there's final volume, there's initial volume. We've added in that heat. The pressure is remaining constant, and we have a flat graph. Okay? Now, I've colored in underneath the graph here because it's going to tell us something on a pressure versus volume graph. Let's look at that. Over here, we know that P equals F over A. P equals F over A. So F equals P times A. That's it right there. Force, if we're talking about work equals force times distance, right? So work over distance what? Oh, got it. Got it. Okay. Thank you. Okay. Pressure equals force over area. Okay? Solve for the force equals PA. Work equals force times distance. Force equals work over distance or displacement. So we can take this and plug it in for our force. So W over D equals PA. Now, if we multiply through by D, we want to get rid of that on this side. We have W equals P times A D. Well, what's area times displacement? Volume. So work equals pressure times volume. So if we find the area underneath this curve, we have found the work. So in this case, we've found the work done by the system, not on the system, right? Make sure that you notice there's a difference between those two. Okay? All right, and that'll stand true for all the graphs we look at. So it says here the pressure is held constant by the external atmosphere and the weight of the piston on the block. Work equals pressure times change in volume. The work done is the colored rectangular area underneath the graph. And in this sample, work is being done by the system. So, if that's the case, what is W going to be for us? Work is done by the system. W needs to be negative. That's right. Because we want delta Q to go down. Right? Delta U to go down. So make W negative. So you kind of, well, that would do it, right? Okay. All right, here we go. Isochoric. Pay attention now, gang. I know you're getting tired, but hang with us, okay? All right, isochoric. Here's constant volume. So if I put a flame underneath this container, the volume isn't changing, is it? It's staying constant. Maybe it's a paint can. It looks like a paint can to me. It's a paint can. There's just gas inside. We heat it up, there's going to be a great pressure increase, isn't there? So when pressure increases and we don't let the volume change, we end up with a vertical line. As soon as you see that, you should be able to say, oh, that's isobaric. Sorry, isochoric. Okay? That's isochoric. Now, what is the area under this line? None. So what's the work done? Zero. So what does the change in energy equal? No. Q. It equals Q. Right? Because look, our formula here is delta U equals Q plus W. Well, in that graph right there, there's no work. So that's zero. So delta U equals the Q, equals the heat input. Folks, if you know that, that could be a really easy answer that you could get right on the AP exam. Just take a peek at that. So now U equals Q. Right? Okay. Now, next one. Here's isothermal. Okay, so now we're constant temperature. Okay? So we're getting a change in pressure and we're getting a change in volume, but the temperature is staying the same the whole time. Temperature is staying the same the whole time. So if you took your pressure and your volume here, PV equals nRT, and you went in and solved for T all along this line, you're going to get the same answer every time you solve for it. Constant temperature. Okay? The water here is helping us with this. So what we're doing is as we're expanding this hand up here, if you can see the hand, is slowly letting that piston move up. Well, if it slowly lets that piston move up, then what's going to happen to the temperature inside that container? It's going to go down. So we don't want it to do that. We want it to have a constant temperature. So as that hand releases the pressure, heat's being put into the system to keep the temperature the same. Okay? So, if we know that the temperature remains the same, you had a question number 8 on your multiple choice. Said the kinetic energy of these two things stayed the same. Why did it stay the same? Because it was in a room of the same temperature. Mr. Cox said earlier, when you have the temperature the same, the internal energy stays the same. It's dependent upon the temperature. So if I don't let that change, what happens to W? What is the change? There isn't any. If there's no change in temperature, there's no change in U, is there? Which means that Q is going to equal negative W, right? Q is going to equal negative W when we move it over. And then, you're going to have to adjust the signs. Make it work. Okay? All right. So it says the internal energy remained constant throughout the isothermal process. Therefore, the change in internal energy, delta U, equals 0. That's important. Isothermal. Remember that relationship between temperature and U. Okay, the last one here is adiabatic. Adiabatic. Adiabatic, we're not going to let heat in or out. Here's our graph. Now, a lot of times, you're not going to have these blue temperature lines on here, right? So this graph looks awful similar to that one, doesn't it? Well, how do you know the difference? Well, if you solve for T here and T here, they'd be the same. If you solve for T there and T there, they're not the same. Okay? So that's the difference between the isothermal and the adiabatic. It says here, because the chamber is insulated, there is no movement of heat into or out of the chamber. So what up here is 0. Q. There's no input of heat. So if that's the case, we don't input any heat. How does delta U compare to W? They're the same. They're the same. So whatever, because we're not letting heat in or out, whatever work we do on the system, or whatever work we let the system do, is going to directly affect the change in internal energy by the same amount. If the system does work, the internal energy goes down. If we're doing work on the system, the internal energy goes up. Okay? All right, so down here, it says as the chamber is allowed to expand, the pressure and the temperature decrease. And as the chamber is compressed, the pressure and the temperature increase. Right? Because we're pushing down on it. Mr. Cox, do you have anything you'd like to add?
You done with this stuff?
Yes.
Okay. Guys, what we want you to do right now is get the package that I gave you, not the crash assessment, the package. Okay? Go ahead and do the section where it says terms and processes. Go through and answer the questions. And also, flip the page, you'll find the 1979 question on thermal processes. Okay? We want you to do that.
That one was on Mr. Miller's AP exam when he took that one.
AP question from 1979. Obeying this relationship, which means temperature must be constant.